So, as we said in the previous lecture about this development length, it's going to be that length needed to transfer the force in the tension rebar or compression rebar to the surrounding concrete. So you cannot just sub the bar at the point that you don't need it, at the point that you assume that the moment here is going to be equal to 0 because you have some moment that's going to be causing tension in the previous section, and this force in the rebar needs to be transferred or developed to the concrete. So as you see here at the end, instead of just stopping the bar, we have this hook. So we can sometimes hook the rebar, or sometimes we can provide this development length. And we give this example here. At this point here, you don't need the rebar. It's not needed. Both of these two rebars, the Y rebars, are not needed, but you cannot stop it right here. You need to extend for this L sub D distance. We went through some equations for L sub D, and we said it's going to be pays this L sub D. You're going to have here a constant. You're going to have the yield strength of the steel, of the rebar, concrete strength, whether you have lightweight concrete or no like normal weight concrete. We have some factor based on having this to be top rebar, bottom rebar, or vertical rebar. We have a factor for the epoxy coated. We have a factor for the size. We have a factor for the clear distance between the edge of the concrete and between the rebar itself. And of course, we have the bar diameter. For this CB, we have taken here a couple of examples, right? We said CB for this rebar is going to be this CB1 or this CB. And of course, that one was controlling because it's going to be 2-inch typical every place. For this rebar, we needed to compare CB2 with CB1 and take the smaller of the two. So this straight development length is good. I mean, for certain distance here or certain length, you should be able to transfer the force from the rebar to the surrounding concrete. The problem is going to happen at certain locations, and this is where we're going to start today's lecture. Slide set 14. Problem is going to happen, if I may just skip and go here to this example, is going to happen in a case like this. In this case, this can be the end of the column. So in this distance here, in this length through this L sub D, you're good on this side. You don't see here a problem. But when it comes to the column side, if you have any tension in the rebar here, you need to transfer it to the concrete. So within this column, you need to provide this L sub D. And the column size is only 24 inches. Don't forget that this gives you a column like this. So you don't have this to be extended. You don't have another back span. You don't have another span of the beam that you can just put the rebar through and say, now I'm going to be developing this rebar on the other side. All what you have is only 24 inches. But when you run the analysis, you see that L sub D needed for this rebar is going to be more than 24 inches. So it seems to me here that the straight development length is not a good idea. Let me go quickly through this example, and then after this, once I reach a certain point, I'm going to go back and start from the beginning of this slide set to show you different hooks and why the need for a hook instead of a straight development length. In this beam here, they give you top rebar that you are trying to develop. You have tree number 8, and then we have the clear distance. We have everything very similar to the previous example. Concrete strength is given at 3,000 psi. And then we have the side covers give you 2.5 inch. And the yield strength is going to be 60,000 psi. So I'm going to be going through steps very similar to what we have done the previous slide set. We'll figure out the case of D. If you recall, case of D is going to be basically this equation here. If I may just bring it from the previous slide set so that we don't forget what's case of D. This is going to be here case of D. Disregard lambda in this case. So we have case of D from one of the tables that also went through last time. Just to remind you, here's case of D table, which is 3 divided by 40 Fy divided by square root of F prime C. So you have two options. One option, if you have the values here, it's going to be simple. You just read it off the table. Or let's say sometimes this can be like concrete to 4,500 psi, and in this case, you cannot really use this table. So the best way, just use the equation. So here's what KD stands for. And then we know it's going to be top bars because you have more than 12 inches of concrete below the top bar. It's going to be psi T, it's going to be 1.3. For the size here is number 8, and we have certain psi values. So we have the values here for psi, and here's psi s. If I may go back to the previous slide and show you the values for psi, let me get to it. Psi sub s, when you have the rebars number 6 and smaller, it's going to be 0.8, number 7 and larger is going to be 1.0. In our case here, the bar size is number 8, so it's going to be 1.0. And then we have this product of psi sub t times psi sub s is going to be maximum 1.3. Now it's going to be 1.3, or max or cap is going to be 1.7. This is good. Just use the 1.3. We have the CB value, which means cover from the rebar to the edge of the concrete. We figured it out to be 3 inches. If you like to discuss this more, if you have questions, I guess we should be able to go back to this slide set and see definition of CB and which one to consider. It's going to be this CB1 or CB2. Of course, we're going to be taking the smaller. So here we go. We have 2 values for it, and this one controls. We're going to be using here 2 inches. We said usually this value of KTR we usually consider to be 0, just for simplicity, which is this KTR. Assume usually to be equal to 0 for simplicity, right? We say conservatively is going to be equal to 0. And then this factor here is going to be maximum of 2.5. So we try this number here, set KTR to be 0, CB is going to be the 2 inch, and DB number 8 is going to be 1 inch. With that, this factor here is going to be 2, this is in 2.5. This is good. We move forward, we use our equation, and guess what's going to happen? Now, you end up with 53.4 inches, like 54 inches. And we have also a minimum length of 12 inches. Now let's try to put the rebar. How much is available for you? Only 24 inch. But this rebar needs to stick here to be 54 inches. I don't think that it's gonna be okay just to leave the bar to stick this way. And also it's not a good idea if I'm gonna come here and do kind of a block at the end of the beam. You don't wanna see this, right? You don't wanna have a piece of this beam that sticks beyond the column. This here, the building ends here. So you cannot really have this piece to be part of the beam and just stick it out because you need to contain this rebar and put it in some concrete. Not a good idea. So what is the other option? Other option, instead of having this straight development length, we could write a hook. Now let's see what type of hooks are available for us. I'm gonna go here and start from the beginning. I'm gonna say we have here 3 types of hooks. We have this standard 9-degree hook, we have a standard 180-degree hook, and then we have the 135-degree hook. Difference between these 2 hooks when it comes to performance, close to each other. And as you see here, if you're going to be doing this 9-degree center hook, you need to extend this rebar, the tail, for this free end, you need to extend for 12 dB. And if you're going to be doing this 180, this is going to be coming here like 4 dB from the center of this rebar. You imagine that you have here a rebar or something, like a die that you put this around it. And this rebar size compared to this rebar size is going to be 6 times this rebar size. So you have certain detailing requirements that we need to follow here. So we know what's the 9-degree hook, we know what's the 180-degree hook, we know what's the 135-degree hook. The 2 common ones that you're going to see in beams and columns is going to be the 9-degree and the 180. If there's a chance to do the 9-degree, do it. Don't do the 180, because 180 needs a little bit more work in the machine, right? You need to have a bender, like a bender machine. And in order for you to do this, it's going to take a little bit more effort and time. And also, in some cases, if you bend the rebar this way, you may end up by having some cracks right here in this location from the top, because here you are putting the rebar in tension. So you may end up by damping the rebar. So you don't want to do this 180 degree as much as possible. You'd like to avoid this. Okay? So in many cases, 90-degree center hook is give you the option that's available for you, and this is what you'd like to do. Okay. So what's next? Now I'd like to see, am I gonna have the same equation or do we have different equation? What equation? I'm talking here about this LD. Here's L sub D equation. How about when I have a hook? How much development length do I need for the hook? And do I have equation for it or not? I'm gonna say yes, we have it. Here is the LDH. Instead of calling it L sub D, like for straight development, so this L sub D development length, can have LDH, development length for the hook. Is going to be measured from the point that you don't need the rebar at, and then after that you extend it for this L sub DH to the end of the rebar itself. You can have 180 degrees or you can have 9-degree hook. Both of them, you're going to end up with the same thing, that we call here LDH. It's going to be the same value. Here's the equation. Now compare it with the straight development length. Much simpler. Just says here 0.02 psi sub E for epoxy, F sub Y, lambda, lightweight concrete, concrete strength, rebar size. For psi sub E, I have only two values, 1 or 1.2. If you remember, for the straight development length, I have three values, 1, 1.2, 1.5. Let me put this here back so that you guys remember what we're talking about. Here's for the epoxy, 1.5, 1.2, and 1.0. For the hook, it's going to be only two values, right? 1.2 and 1. Lambda is the same thing for the lightweight concrete. The lightweight concrete factor is going to be equal to 0.75. In the case of the straight development length, we have the minimum LD was equal to 12 inches. In here is going to be equal to 8 times dB and 6 inches. This length, again, is going to start from at the point that you don't need the rebar at till you end up with putting the hook, the end of the hook, from here to there. Meaning the distance is going to be at least 6 inches or 8 times this rebar diameter, 8 dB. I have some multipliers. So after you're done with this LDH, you're going to have some multipliers, like multiplier 1 times multiplier 2 times multiplier 3 times multiplier 4 times LDH. And this is going to be the final LDH. You just multiply them all by each other. The first multiplier happens to be equals to 0.7, and this happens when you have number 11 rebars or smaller, which most likely all the rebars that we use. When the side cover is going to be smaller than 2.5 inch, and for 9-degree hook with cover on bar extension beyond the hook is going to be smaller than 2 inches, not less than 2 inches. So we're going to see some examples just to make it simple for us. You have another multiplier, is going to be 0.8 when you have 9-degree hooks for number 11 and smaller. And this is going to be either enclosed with ties or stirrups perpendicular to the bar, being developed, spaced not less than 3 dB. So actually, when you have this multipliers, you should be happy because the needed LDH is going to be smaller. So all of this means that you have a good situation. The spacing between the bars is going to be large enough. The concrete cover is going to be big enough. And did they give you conditions here when you have 9-degree hook or 180-degree hook? We have also this multiplier, which is very similar to LD for the straight development length. If you don't really need the rebar in your design, and maybe you need 50% of the trends to be in this rebar, so you can reduce it, but let's say 50%. So it depends, do you really need all of this rebar in your design? Or you just added few rebars and you don't need it at this section? Let's give you more reduction here, reduction item D. Now, going back to the example we started with, you have the column of 24-inch, and then you have this information about the rebar. You have the rebar size, the location, you have CB, and then we tried first for L sub D. When we did L sub D, it's supposed to be, let's say, 54 inches. But the available distance here is only 24 inches, so this is not a good idea. So the good idea that I'm trying here to do is to use a hook at the end of the rebar and see how much is this LDH. And if this LDH plus the concrete cover is going to be within 24 inches, I'm going to say this is great. I don't need to add this block at the end of the beam. It's going to look, I mean, it does look nice. You're going to have a piece here of the concrete that sticks out of this column. Not good. So I'm going to be using this equation that we just introduced today. 0.02, no epoxy mentioned, is going to be 1. 60, lambda is 1, normal with concrete. Strength of the concrete 3000 times 1, because it's going to be number 8. The rebar size is going to be 1 inch diameter. You end up with about 22 inches. So, okay, good, 22 inches, promising. Let me go back here. But I have here 24 inches. So I'm going to have very small cover. So let me be sure that I'm going to be okay, especially that I have some multipliers. If you guys remember these multipliers, let me try to use them as much as I can. So, okay. What multiplier are you talking about? I'm going to say this is going to be the first modification factor or first multiplier. It says for number 5, for number 11 and smaller, when the side cover is going to be more than 2.5 inches, you're going to be using a factor of 0.7. I don't have here any ties, so I cannot have here any reduction for this 180-degree hook. I'm going to take you back here. I don't see here any ties inside the column. I'm not talking about these ties. These ties are good, and you're going to be using here within the beam itself, right? Because someone's going to be looking at this and say, but you have ties. I'm going to say, usually this tie is going to stop right here. Look at the last tie. They do it here in blue. You see this? Here's another one. Here's another one. No beam ties is going to be running inside the column. So I don't really have this luxury of having any reduction for this 180-degree hook when I have ties around it. So the only reduction I'm going to have is going to be the 0.7 based on the side cover. If the side cover is going to be more than 2.5 inches to that specific rebar, you can use a reduction of 0.7. So when I use 0.7 times 21.9, now I end up with 15.33 inches. Now let me check here the geometry of the beam and whether it's going to be okay or not. When you check the minimum here, it's going to be 8 times dB or 6 inches. So I said, great. 8 times dB is going to be 8 inches. 8 inches more than 6 inches because I have here 2 minimums, right? But based on this analysis, I need to have about 15.33. You can say at the end, I'm going to be adding here 2.5 inch cover, right? Plus 15.33. Yes, this is going to be the minimum, right? This is great because now I'm going to be within this 24 inches. So what is the actual length that I provided here? You see, the actual length is going to be 24, subtracting 2.5 is going to be actually 21.5 inch. So the needed development length for the hook is 15.33. I provided 21.5 in my details. So when I put my details here for construction, I used this rebar to stop at 2.5 inch from the end of the column, meaning that I have provided LDH of 21.5 inch. You added 2.5, now you end up with 24. The provided length here turned to be larger than the required length for LDH. So this is great. We're good. There is no issues with this design, and I was able to do a hook instead of adding a block here of concrete at the end of the beam. If you remember, if I'd end up with a straight development length, you'll need to add this block at the end of the beam. So we don't really need to do this. Otherwise, someone's going to say, this building from this side here looks ugly because it's going to be too much work for us. We're going to have maybe a wall right here. Why do you want this piece to stick out like this? Any questions?
since we had so much clearance, like we needed 15, but we were able to squeeze in 21.
Yeah.
Would we try a 90-degree hook, or like just to see if it would fit?
Yeah, you can absolutely. 90-degree hook is gonna work, but let's check something here. Do you have any reduction for the 90-degree hook? Anything here?
Does the first one apply?
The first one? Do you have an extension? Bar extension beyond the hook, not smaller than 2 inches?
What's a bar
Do
extension?
you have a
again?
cover? Okay, so it's gonna be 0.7. The bar extension means beyond the hook is gonna be smaller than 2 inches. You know, the bar extension beyond the hook.
Oh, okay.
Which
Yeah.
means this 21.5 subtracting the 15.33. So you have it, right? 21.5 minus 15, let's say, and half, you're talking about 6 inches. Because originally this hook is supposed to stop here, somewhere here, right? At 15.33. And the question is, do you have a little bit more space? So I'm gonna say, yeah, 9-degree center hook would work here because you're gonna end up with the same multiplier, the same 0.7. But here in this example, just so you know, the reason that I use 180 degrees because it was just mentioned in this example. But 9-degree hook would have worked beautifully here in this example.
Okay, got it.
Yeah. All right.
Thank you.
No problem. So now let's talk about the splice. What does it mean by splice? A splice means here's one rebar, and this rebar you cannot really build your beam this way because the rebar is just very long. And it's gonna be very tough to handle this long bar. I mean, how would you carry it? How would you put it in place? How would you put it within the ties and tie it and carry it and the whole thing? So what do? They just do this lap splice. There is no weld between the two. So actually you can have a little gap between the two. You can have one rebar to be here. Let me draw it this way. And the other bar is gonna be right here. And you can leave a little bit of concrete between them. And this concrete is gonna be, let's say, about an inch. They call this non-contact lap splice. When they touch each other, they call it contact lap splice. So I want to be sure that you guys understand there is no welding between the two. We are not welding the two rebars to each other. But what you started with, you have some tension bar in this rebar here, and you'd like to transfer it to the other bar. How it's going to happen? Now, this tension force in the rebar is going to be transferred to the surrounding concrete. Now, the surrounding concrete is going to be taking this tension and then delivered back to the other rebar. So you start here with some tension force, right? It's going to be going through the rebar, and at each little segment of this rebar, you're going to have transfer of this tension from the steel to the surrounding concrete. Concrete is going to be taking this and delivered back to this rebar. And with that, you splice it, which means that you transfer the force from this side to that side without welding these two rebars to each other. So this is kind of similar to the concept of this straight development length. I cannot do here any hooks when it comes to splices, right? The code says this lap splice length is going to be equal to 1.3 times the development length that you have determined, the straight one. So if you take this equation that we have used in the previous slide set, in slide 13, just take this number here, after you're done, multiply by 1.3, you're done. And also you have this condition, says the minimum length for the lap splice is going to be 12 inches. So this is going to be minimum of 12 inches. Whatever number that you're going to end up with, compare it with 12 inches. I'm sure that any number that you're going to get is going to be maybe more than 2 feet. So for number 5 rebars, usually we do 2 feet and 6 inches, just so you guys know. So 12 inches is really very low compared to our analysis here. One example, you have this simple span, uniformly loaded beam, number 7 rebars for the tension reinforcement. effective depth D is going to be 18 inch. Determine where the bars may be stopped. F prime C is going to be 4,000. Fy is going to be 6,000. And it says here AS required is going to be the same as AS provided or furnished is going to be 3.6, which means I don't have here any reduction factor because the required is less than what is needed in the rebars. No, this is going to be right there. And it says here, assume that you have normal weight concrete. The stirrups extended to the end of the beam at the support. I guess you guys know what's the reason of this, right? Because if you have it going through the support, you can have some reduction factors. The bars are uncoated, conventional rebars. And then we have here a section in the code that says this rebar needs to be extended in a rebar at the point that you don't need it. You need to extend it at a distance is going to be the greater of the two values, either the depth D or 12 dB. When you think about most of the rebars that we use, let's say maybe number 8, number 9, number 7, we're talking here about 12-inch depth, right? 12 times dB is going to be 12 inches. When you look at the depth of most concrete beams that we use, usually this depth is going to be maybe 18 inch at least, right? 24 inch. So this number usually controls your reinforcement details. It's not going to be this number. This is going to be the most controlling one. So we draw the beam, uniformly loaded, as I said. Here's the moment diagram, and here's the span, and here's the section through the beam. Are you guys following me? Yes?
Yes.
Okay, very good. We have here 6 rebars. I don't know the exact value of the moment, but this is not critical to me. But I know that this moment demand, because it's going to be the demand, is going to be equal to the capacity. As it says here, this is going to be the required, right? They said AS required is going to be the same as AS provided, 3.6 inches. So whatever we need, we're just able to provide it. So capacity here matches the demand, exactly. So Phi here equals M sub U. Someone's going to say it doesn't happen, right? In real life, I'm going to say yes. In any design example, you cannot really have this, but just happen here for this example, for the sake of discussion. So they give me here 6 bars. So I'm going to say here that if I just throw a number here, I'm going to say if the capacity or the demand is going to be equal to 120, is this a good number that you can work with? I'm going to say yes. 120 what? kfoot. Okay, this is going to be M sub U, which is the same as M Phi M. How much each of this rebar do you think is providing in terms of this M sub U in this trend? Any idea? Yes? Are you guys following me?
Can you repeat it one more time, please?
If the demand is equal to 120 kfoot, and the capacity is going to be equal to the demand, Phi equals also 120 kfoot. And I have here 6 bars. Can you tell me how much is the contribution for each of this one of the 3 bars with regards to this Phi?
20 kfoot.
20. Yeah, how did you do it? You say, okay, the total is going to be 120 divided by 6 bars. So each bar would give you 20 kfoot, correct?
Yeah.
Okay, good. Now let's draw here the moment diagram. So what is that moment diagram? The curve? This is the demand or the capacity here? Is this the capacity or the demand? Demand, thank you. Thank you, Venus. So this is going to be here the demand. Because it is different from a point to a point, this is going to be W ultimate, right? M ultimate. And the capacity, if you keep this 6 rebars straight from the beginning to the end, your capacity line is going to look like this. Because your maximum moment here is going to be equal to the maximum moment demand is going to be equal to the capacity. It's going to be the same as 120. So I'm going to say this point here means right at this point, right? It's going to be equal to 120 kfoot. This line here, this height from here to here is going to be 120. It means for each one of these segments, you're going to have 20. You have here 20, 40, 60, 80, 100, 120. You guys agree? Yeah? Make sense or no? Not very clear. Yes? No?
Yes, makes sense.
Okay. So this here represents each one of this segment or height or distance or this ordinate represents 20 kfoot, which the contribution of each one of those 3 bars. So when you look at this, someone's gonna come here, you know what? Let me go at this point. What happened here at this point? I'd like you to have a close look. Try to understand. He's gonna say, in my opinion, at this point, I just need 2 rebars. Correct? I don't really need 6 rebars. So why would you provide here 6 rebars? Someone else is gonna say, how about this point? If you like the top 2 rebars, the top 2 rebars, you don't really need them because look what happened. Your demand is coming down. Now your demand at this point, 4 rebars is gonna be enough to support it. See this point here? It's gonna be your capacity line, right? If you have only 4 rebars, it matches or it intersects with the demand line. So at this point, you're gonna say, I need only 4 rebars. How about at this point, you say, I need only 2 rebars. So good. So if I like to provide the rebars, I can just put here 4 rebars from this point to this point, right? You guys agree? So as long as you're gonna be at this section, I need here how many rebars? I'm gonna say at this section, I need 6 rebars. Right in the middle. 6 rebars are needed. Say, how about at this point here, coming down? You can say in this point coming down, I will need right here. I will need 4 rebars. How about this point here coming down? I'm gonna say here, I need 2 rebars. But I cannot just stop the rebar right here. I need to extend it a little bit. You have LD, and what else do you have beside this? You're gonna say, I have this number here that I mentioned, which is gonna be equal to the depth or 12 dB. Now, where is the LD can be measured from? Someone's gonna say, I can measure the LD from here. And after this, I'm gonna be extending it to a distance of D. Now, if I'd like to put the rebars, I'm gonna put it here in different color. So let's do it here in blue, let's say. I'm gonna put the first 2 rebars from here to there because I need 2 rebars, right? At any section of this beam, I need here 2 rebars. I'm gonna put additional 2 rebars right here, but I'm gonna make it a little bit shorter from here to here. I'm gonna put additional 2 rebars. It's gonna be shorter from here to here. Of course, they're gonna be on the same level, right? They're not on the top of each other. I'm just showing it this way, just for illustration. So this is gonna be the rebars I have. So right in the middle, how many rebars do you guys have? Because each line here represents what? 2, 4, 6. How about right here? How many rebars do you have? We're gonna say I have 2 and 2, they're gonna be 4, right? How about here at this section here at the end? You can say I have only 2 because each one of these lines represents 2 rebars. Are we good? Any questions?
No.
Okay, great. All right. So my problem here, where does this point happen? What point? I'm going to say where that point, if I may put a very small circle here, where does it happen? Where does this point happen, right? At which demands going to be equal to some capacity related to 2 rebars, 4 rebars, and 6 rebars. Well, I know the equation of this curve because this equation is going to be like double degree parabola. And in this case, you say, if the distance x, this is going to be the distance x, right? Measured from the center line, from the center of the span. If this measured distance x, this is going to be your y. So this is going to be x1, this is going to be y1, x2, y2. x3, which is what? L over 2, 1/2 of the span. The total is 24 inch. Now this becomes here 12 feet. Excuse me, I said 24 inch. 24 feet, half of it is going to be 12 feet. And this y distance is going to be like the 120 cubic foot I was just talking about. But actually the value is irrelevant because you can just solve it by the ratio of y1 to y2 to y. What's the ratio of y1 to y2? It's going to be 1/2 of it, right? This is going to be 2 divided by 6. And this y2 is going to be 4 divided by 6. And this y is going to be equal to 6 divided by 6, which means 100%. So I can just do it by ratio. Since this is going to be here second degree parabola, I can say x1, right, divided by L over 2 squared is going to be equal to y1 divided by y. I know that y1 divided by y is going to be 1/3. I know that this is going to be 2 rebars versus 6 rebars is going to be 1/3, right? 2 divided by 6 is going to be 1/3. Now, based on this equation, I should be able to find out this location of x1. So x1 here is about 7 feet. How about x2? Can someone help me with this x2 for quick? Yes? This is going to be x1. You're going to take it out, remove it, put instead x2. So I'm going to say this is going to be here x2, right? And instead of 2 rebars, put 4 rebars. How much is this x2 in this case? $9.8, great. Right, thank you. Here it is, 9.8. So this distance here is going to be 9.8. So what you need to add to it is going to be either D or, let me look at this. Let me put here a box so that you guys remember this. It's going to be either D or 12 dB, the greater of the two. And most likely it's going to be D. Why? Because look at this example here. D is how much? 18 inch. 12 times number 7. Let's say even if it's like an inch, it's going to be 12 inches. So 18 inch. So it's going to be adding 18 inch to it. So after you're done with this rebar here for the 7 feet, you add 1.5 feet to it. It says here 18 divided by 12 is going to be 1.5. You ended up as, let's say, 8.5 feet. So at the distance from the center of the beam, you extend this rebar for 8.5 feet in both sides of it, and then you can stop it. So in this case, we are looking here to reduce the amount of reinforcement that we provide throughout the entire length of the beam. And then with the way that we think about it, we say, if you don't need the rebar here for the strength, don't use it. Just cut it at this point. But you need to extend at least a distance of D distance from this cutoff point. So as it says here, after this cutoff point, I need to extend it for D distance. D here is 18 inch. Compared to 12 dB, of course, this is going to control your design. We repeat the same thing here for the second point. For the second point, we said the distance is going to be 9.8. You're going to be adding 1.5 feet to it. You end up with 11.3. So someone here is going to come and say, 11.3 is going to be very close to 12 feet. Why don't you just keep it straight? I'm going to say, yeah, absolutely. So there is no need to stop additional 2 rebars at this point. I just extended because after the extension that I was just talking about, look what happened. I'm almost right at the end of the beam. So it doesn't mean anything. You're at 11.3 and this gave you here 12 feet. It's only 0.7 for a foot. You're talking about 6-7 inches. So it's not worth it. Just keep the rebar straight to the end. And maybe it's going to be a good idea to stop 2 rebars at a distance of, as it says here, 8.5 feet from the center. So at the end of the day, you're going to have 2 rebars running from here to there. Additional 2 rebars running from here to there. So you can call them here 4 now. And then 2 rebars give you running from here to there. And of course, you extended 1.5 foot from each side just to follow this requirement of the code. So, okay, good. At least you start here to reduce the amount of steel that you're using to save a little bit. Now, you'd like to see here, how about this, L sub D? I mean, L sub D starts from here. Do you have enough development length for these 2 rebars? I understand that you're going to use here 8.43, but is the L sub D is going to be within this 843 or is going to be more? Because if L sub D is going to be more than 8.43, it means I need to extend the bar more. So I'm hoping here that LD is going to be smaller than 8.43. So I'm going to try this. So what I would do here, I'm going to run and try to find out the development length for this rebar, for the bottom rebar. When we do this, if you look here at the analysis, you end up with how much? It's going to be 26.5. So let's say about 30 inches. Just trying to be here generous, right? 2.5 feet, right? Compared with 8.43 feet. So this is great, right? You don't really need to extend the bar. So the conclusion here, or what I'm trying to drag your attention to, the calculation of LD is measured from here. It's going to be measured from this point, right? And the actual development length provided is going to be this length, which means 8.43 or 8.5 feet. Because no one's going to do it for you as 8.43. At the end, you provide this to be 8.5 feet, right? If your L sub D is going to be within this 8.5 feet, you're good. If L sub D is going to be larger than 8.5 feet, you need to extend the bar more to cover L sub D, not just L sub D and this type of cutoff points plus the D distance. Any questions? You're good?
Not seeing how you get the X1 to be 2 bars over 6 bars. I don't really see it on the picture.
Okay.
How you
Right.
get.
No problem. No problem. No. All right. Do you have any issues with this equation? Is it clear or not really?
Not really.
Okay, this is second degree parabola. So it means that let's say if x is going to be 1, y is going to be 1, if x is going to be what? 2, right? Y is going to be equal to 4. You follow that? When you have second degree parabola? Yes?
Okay.
No?
Yeah.
Okay. Meaning that y equals to x squared, right?
Yes.
So when x again is equal to 1, y is going to be equal to 1. Yes. When x is going to be equal to 2, y is going to be equal to 4. Put here x is going to be, right? So y is going to be equal to x squared. So let me put the equation here. You can say here y equals to x squared. Again, let me put here x of 1, y of 1, x of 2 is going to be y of 4, and so forth. I say, okay, good. Now, if I have 2 points on the same curve, and I have this equation, I guess I should be able to come up with this relationship. You do x1 divided by this total length, right? Squared is going to be equal to y1 from here to there divided by the total or the uppercase y. Yes?
Okay.
Okay.
Yes.
So in this case, I'm thinking here, what does it mean by y? Do I have units for it? When you look here in the problem, there is no fee, man. I just threw this 120 just for sake of discussion so that we understand if I have 6 rebars, this is gonna be like equal ordinates or equal values for the moment, right? And each one of them is gonna be equal to 20k foot. Okay, now it makes sense. Now let me go back here to this slide. So I'm gonna say, in this case, the ratio of y1 to y is equal to what? You can say this looks like for the height it's gonna be 2 segments divided by the height of 6 segments. 1, 2, 3, 4, 5, 6. So actually, each segment represents a bar. So I'm gonna say it's gonna be 2 bars from here to there, 1 and 2 divided by 6 bars. This is the reason that I say 2 divided by 6. Or you can say the ratio of this y1 to y uppercase is gonna be 1/3. And you can look at it. This is gonna be like 2 segments versus 6 segments. 2
Okay.
bars divided by 6 bars.
All right, thank you.
No problem. Any more questions? Otherwise, I just let you go. You guys have a good night.